then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great.
Tis the season to be serving.
When I was solving equations, I was feeling amazing. Greetings, Precalculus students, and welcome to lesson number 3. So lesson number 3 is about domain of functions. So on today's agenda, first thing we're going to do is we're going to review graphing piecewise functions. We'll also do a review of evaluating a function from an algebraic standpoint, and then we'll look at the domain of functions. And when we look at the domain of functions, we're going to express those domains in interval notation. So that's kind of what we have going today, and let's go ahead and begin our review. All right, so let's review graphing piecewise functions. Piecewise functions. Again, it's a function consisting of 2 or more pieces based on several conditions. So let's say our piecewise function, I'll call it f of x. And let's say the first piece is x squared minus 2x minus 2, provided x is less than or equal to 2. And let's say the second function is 2, provided x is greater than 2. So that's my piecewise function. And what I want to do for this, I just want to graph it. I'm not overly concerned about evaluating it. I think that's pretty straightforward. If I want to evaluate, if I evaluate it at a value that's less than or equal to 2, I'll use the top piece. If I evaluate it at a value that's greater than 2, I'll use the bottom piece, meaning the answer would be 2 for all of those particular values. But I want to go ahead and graph this. Now, again, I have a horizontal line here when f of x equals 2, and I have a parabola here. Now, graphing this parabola the way it's written right now, maybe a little bit difficult. I think it's probably easier to graph this guy when putting it into vertex form. So I'm going to go ahead and express this parabola in vertex form. So x minus 2x, x squared minus 2x minus 2. This is just one piece of this function f of x. Now, for the sake of just calling this something, I'm going to call this particular piece of f of x, I'm just going to call it h of x, just to be able to call it something. And I'm going to express this in vertex form for a parabola. So I'm going to do a process called completing the square. And what I'm going to do is take half of the coefficient of x and square it. That would be negative 1 squared, that's 1. So I'm going to add 1 and also subtract 1 so I don't add anything to the equation. If you're unfamiliar with this, this is something that should have been taught to you in a previous algebra class, either algebra 1 or algebra 2. But if this seems somewhat foreign to you, there will be a video covering this stuff a little bit later. So anyway, to express this in vertex form, if I factor these first 3 guys, this would be x minus 1 squared, and then minus 1 minus 2 is minus 3. So we have a vertex of 1, 3 for this particular parabola. So I have a vertex of 1, 3, and then I can just plot a couple of other points. I'm calling this the function h of x. I can plot a couple of other points to do its graph, and this has a vertex at 1, -3. I didn't see the negative sign there. Not sure if I said -3 or if I said +3, but it should be at 1, -3. All right, so let's go ahead and graph this. So I'll graph the top piece first. Now, again, the top piece, this piece that I called h of x, is only for numbers that are less than or equal to 2. And it's less than or equal to 2. So this function will have a closed circle when it stops at 2. So let's see, this function has a vertex at 1, -3. So that's 1, 1, 2, 3. There's the vertex of this particular function. And then I just want to choose 2 points, 2 other points, a point to the left and the right of the vertex. So let's say I want to find the value when x is 2. That's 1 to the right of 1. So I want to find h of 2. Now, it's probably easiest to find h of 2 in this vertex form versus this non-vertex form, because if I look at it, this is 2 minus 1, which is 1, squared is 1, 1 minus 3 is negative 2. So I have a point at 2, negative 2. So let's say this is 2 right here. So I have a point on 2, negative 2, which will be right there. Now this point is actually where this graph ends, because again, this graph is for the values of x which are less than or equal to 2. But because it says or equal to, I have a closed circle right here. If it just said less than 2, I would have to make an open circle on that particular point. And now I just want to put one more point for this parabola, and I want to go 1 unit to the left of 1, so that of course would be 0. So I want to find h of 0. And typically for a parabola, if you go equal distance from the vertex, the y values are the same. So this should equal negative 2 as well. But I'll plug the number in just to make sure. So if I plug in 0 here, this is 0 minus negative 1 squared, which is negative 1. Negative 1 squared is 1. 1 minus 3, of course, is negative 2. So I have 0, negative 2 there. So that's my parabola. So let me go ahead and extend my parabola. So there he is. Now he stops right here, keeps going to the left, but it stops right here on the right on 2. And then for values greater than 2, the function is just 2. F of x equals 2 is just a horizontal line going to 2 on the y-axis. So 1, 2. So we'll start here at 2, open circle, because this guy doesn't include 2. It says greater than 2, not greater than or equal. So open circle, and then a line. So that's how the graph of that particular function, particular piecewise function, should look. And lastly, one last thing I would like to review before we look at domain of functions. I want to review evaluating functions. So let's say f of x is, I'm going to make this something fairly simple. Let's say f of x is 3x minus 1. Let's say something that simple. And let's say I want to find f of x plus h minus f of x. So f of x is 3x minus 1, and I want to find f of x plus h minus f of x. And you'll realize a little bit later in the course why I'm interested in finding this particular guy here. He's pretty significant. And so you'll learn about this a little bit later. But trust me, there's a reason why I want to evaluate this particular guy here. So I know what f of x is. It's just 3x minus 1. So I know this, but I need to find f of x plus h. So I need to plug in x plus h for x here. So let me first figure out what f of x plus h is. So f of x plus h is 3 times x plus h minus 1, or 3x plus 3h minus 1. So that's f of x plus h. And f of x was 3x minus 1, right? F of x was 3x minus 1. So if I do f of x minus f of h, so this is being subtracted here. So 3x minus 3x is nothing. This 3h comes down, and negative 1 minus negative 1 is nothing. So the answer is 3h. And again, this, you're going to see this on your assignment. This guy, f of x plus h minus f of x, is pretty significant for reasons you'll understand a little bit later. But now let's get into the material for today, which is domain of functions. And again, this is not something that should be a novel concept to you. You should be pretty familiar with this, but I want to explain a couple of things to set this up. And what I normally do in class when doing domain of functions is I ask a couple of questions to set up our domain procedure. And the first question I normally ask, so let me title this domain of functions. So the first thing I normally ask is a question like, what is 7 over 0 equal? So I want you to think about that. What do you think 7 over 0 equals? If you need a little moment to think about it, go ahead and pause the video and then unpause it and rejoin us. Now, I'll tell you the answer choices I normally get. And of course, I'm going to list all the incorrect answers I normally get first. So generally, I'll get something like, some people may say, hey, it's 7. Then I say, can we check if that's true? And they'll say yes. And how can we check it? By multiplying. For instance, if I did 12 over 2 and I said 12 over 2 is 6, I can check that because 6 times 2 equals 12. So if this is the answer, then 7 times 0 should equal 7. But of course it doesn't. And then another incorrect answer people would say would be 0. And so I say, well, can we check it? Is 0 times 0 7? And of course it isn't. And then sometimes we would get some more incorrect answers, a little more incorrect than these. And then people finally come to the realization that there is no number that I can multiply by 0 and get 7, because any number times 0 is 0. So there's no way I can find a number that will multiply by 0 and give me anything other than 0. So no way I can get 7. And then people generally remember that at one point they were told that this is undefined. And that's our first principle for domain of real numbers. Our first principle is, I said domain of real numbers, I mean domain of functions, which is based on real numbers. Our first principle is our denominator cannot be 0. So our denominator cannot be 0. Now, when we're finding domain of functions, we're finding all the values that we can plug into the function and get a real value back. So we're finding all the acceptable values that the function can take. And not all functions can take all real numbers. So some of them have restrictions because certain numbers will cause for one thing, their denominator to be 0. And when that occurs, those functions have restrictions on their domain, meaning their domain is not all real numbers. So if your domain is not all real numbers, we say you have restrictions on that domain. And there are a few things that cause restrictions. The first one we'll look at is the fact of our denominator being 0. So our first guiding principle for domain of functions is that our denominator cannot be 0. So let's look at an example. So I have some function here, a very simple function. I don't have to make these functions very extravagant. So let's say the function is f of x is, say, x to the 7th minus 13x squared plus x minus 98 all over x minus 4. All right, so I want to find a domain of this particular function. Now, some of you may think my numerator looks fairly intricate or complex, and perhaps it is. But it is irrelevant to me finding the domain of the function. So the value of my numerator is not going to affect the domain of the function. It's not going to affect restrictions on the domain of the function, I should say, at least not in this case, not this type of numerator. So again, for right now, there's only one thing that can cause restrictions on our domain for right now, the only thing we talked about, and that is our denominator cannot be 0. So we don't even care about the numerator as far as finding the domain. It's insignificant to our life. What we care about is that our denominator, x minus 4, cannot be 0. Because our denominator can't be 0. We showed before, if our denominator is 0, we get an undefined number. So I just want to solve this for x, of course. So this gives me that x cannot be 4. Done. So our domain is all real numbers except for 4, meaning I can plug every real number in the universe into this function. and it's going to spit a regular number back. It's going to spit a real number back. Except for when I plug 4 into this function, I get a number that's undefined because my denominator is 0. So our domain is all real numbers except for 4. And this is one way you can write it. You can write it like this, and there's other ways of writing it. The main way we're going to look at writing domain of functions is something called interval notation. So I'm going to express this answer in interval notation. Okay. So interval notation is actually an interval. And in fact, to kind of explain it, all real numbers in interval notation is negative infinity to infinity. That's how you express all real numbers. Interval notation is a notation that expresses items in order from least to greatest as you go from left to right. So it just means, this comma just means going on to this number. So we're going from negative infinity to infinity. That's all real numbers. Parentheses on a finite number means a number is not included. And brackets on a finite number means the number is included. Of course, negative infinity and infinity are finite, so they always have parentheses on them. So again, so this is saying all real numbers, but our case is all real numbers except for 4. So we need to write this to show that 4 is not included. And I just said that we use parentheses to show that a finite number is not included. So to write the interval notation for this particular answer, I'm still going to start with negative infinity, but I want to stop at 4 to show that 4 is not included. Now understand what's happened. Again, this is showing least to greatest. So right now I'm showing negative infinity to 4. But this is saying all real numbers except for 4. So this is not yet showing all real numbers except for 4. This is really showing all numbers that are less than 4 as I go from negative infinity to 4. So I still need to show all the numbers which are greater than 4. So we do another guy from 4 to infinity. Now you may say you wrote the 4 twice, but I did, but they have parentheses on them showing it's not included. And these two are together in union, so we generally put this union sign here. And this is how we write in interval notation, that the domain is all real numbers except for 4. So negative infinity to the 4, union 4 to infinity. In fact, in general, if our domain is that x is not equal to k, then the interval notation would be negative infinity to k, union k to infinity. So that should be pretty easy to understand. I do another quick example. So let's say h of x is 3x squared plus 18 over x plus 10. So again, when you find a domain of a function, you're going to concentrate on its denominator because your denominator cannot be 0. And so you would say x plus 10 cannot be 0, which means x cannot be negative 10, which means in interval notation, we're going negative infinity to negative 10, union negative 10 to infinity. All right, so that's how those problems work. I want to look at the second condition, second important factor about domain of functions. So the first one was that our denominator cannot be 0. And here's the second one. So let's say I take the square root of 25. Everybody knows the square root of 25 is 5, correct? And let's say I took the cube root of -8. And the cube root of -8 is -2, right? And we can show both of these. 5 times 5 is 25. Negative 2 times negative 2 times negative 2 is negative 8. Well, what's the square root of negative 25? Think about that for me. And again, I'm looking for an answer that's a real number. When we talk about domain of functions, we're dealing with real numbers. Or, what's the fourth root of negative 16, if you will? So I'm giving you time to think about this. And if you came up with an answer, you're probably wrong, because there is no answer within real numbers to answer this question. So there is no such number. I should say there's no real number. There's no real number here. Now, some of you are familiar with this I value, where I represents the square root of negative 1. And in terms of I, which represents a set of numbers called complex numbers, or you may have heard them as imaginary numbers. In terms of I, this guy would have been 5i, but this I is not inclusive with domain of functions dealing with real numbers. So as far as real numbers are concerned, there are no values, which gives our second principle for domain: values. And let me also point out, notice when I took the cube root of negative 8, it worked out fine. So I can take the odd root of a negative number all day and get a real number back. I just can't take the even root of a negative number. So values and even radicals must be greater than or equal to 0. So that's saying they can't be negative. They have to be greater than or equal to 0. So values and even radicals must be greater than or equal to 0. That's our second guiding principle for finding the domain of functions. So for right now, the only way your domain can have restrictions on it, there are other ways, but for right now, the only way your domain can have restrictions on it if you have to have a denominator or an even radical. That's the only way. So let's look at an example. So let's say f of x is the square root of x plus 11. F of x is the square root of x plus 11. Well, that's an even root. It's an even radical. So to find a domain, I need to ensure that the items inside the radical are greater than or equal to 0. And so if I solve this, x will be greater than or equal to negative 11. So there is the domain there, and we're going to express this in interval notation, of course. Now this is saying x is greater than or equal to negative 11. Think about how interval notation works. As we go from left to right, we go from least to greatest. And remember what causes us to have parentheses and brackets. Now, if x is greater than or equal to negative 11, is the negative 11 included? Absolutely, because of the or equal to. So when I write this in interval notation, where am I going to start? Am I going to start with negative infinity? No, I should start with negative 11. So I should start with negative 11, and it should be a bracket on negative 11, correct? And it's going to go from negative 11 to where? To infinity, of course. So there's that domain in interval notation. So in fact, in general, if x is greater than or equal to k, our interval notation is going to be bracket k to infinity. And of course, if x was just greater than k, our interval notation will be parenthesis k to infinity. So let me look at another example dealing with a radical. So let's say f of x is the fourth root of 2 minus x. All right, so once again, I have an even root, and so the stuff inside an even root has to be greater than or equal to 0. So 2 minus x must be greater than or equal to 0. So if you subtract 2, negative x must be greater than or equal to negative 2. If you divide by negative 1, x must be less than or equal to positive 2. So please remember, when you divide by a negative number, it changes the direction of your inequality symbol. So this is saying that x is less than or equal to 2. That's our domain. So we're going to write this in interval notation. Where do you think we should start? We should start at negative infinity. And where do you think we should end? We should end at 2. And what do you think symbol we're going to put on that 2? A bracket. And should there be anything else? No, it stops right there. It's just numbers less than or equal to 2. So in general, if x is less than or equal to k, our interval notation is going to be negative infinity to k with a bracket. And of course, if x is just less than k, our interval notation is negative infinity to k with parentheses. All right. So real quickly to wrap this up, I'm going to do just a series of functions, several functions, and find their domains quite quickly. So here, let's say f of x is 33 over x minus 1. Here, let's say f of x is the fifth root of x minus 3. Here, let's say f of x is 9x plus 12. And here, let's say f of x is the 10th root of x minus 4. All right, so I'm going to find the domain of these four functions. I would like you to try this on your own, however. So now would be the time to pause the video. And when you unpause it, you'll see me working the problems out, and hopefully our answers agree. All right, so this first function, x cannot be 1. I think that's obvious. So our domain is going to be negative infinity to 1, union 1 to infinity. And it can't be 1 because 1 makes our denominator 0. This second function, the domain is all real numbers. There's no restrictions. To have restrictions for right now, you need a denominator or you need an even root. This doesn't have a denominator, doesn't have an even root. It has no restrictions. There aren't restrictions on an odd radical, only on even radicals. So that domain is all real numbers. Again, if you don't have a denominator or an even root, your domain is going to be all real numbers. And in some cases, even when you have a denominator and an even root, your domain still could possibly be all real numbers. Now this third function, f of x is 9x plus 12. And what do you think this domain is? And it should be all real numbers. Again, you don't have the two things that cause restrictions. You don't have a denominator, you don't have an even root. And this last one, this domain should be 4, bracket 4 to infinity, because this is an even root, and you would say x minus 4 is greater than or equal to 0, which means x is greater than or equal to 4. And of course, that's expressed as 4 to infinity there. All right, so that's going to conclude our first lesson of domain of functions. And these domain problems are going to get a little more complex as we proceed on. So every day we'll kind of look at a new nuance of domain functions. But you have the foundation for right now. And so that concludes lesson 3, and we'll see you next time.
Specialized in science and math, original black men, busting thoughts that pierce your mental, the fierce, ripping your section. Vocal toe-to-toe, impeccable, splitting your back, son. Simple as addition and subtraction, black thought, the infinite relax one.